So what we're going to do here is some circle problems. So first thing I want to address is the concept of rate of rotation. So in our last problem, we didn't actually finish it. I allowed myself to get distracted by other things. So we had our rigid rotating platform going around like that. And we found out that the maximum speed that object on the rigid rotating platform could have without slipping, the max was the square root of mu sub s gr. But the question I asked was about the rate of rotation. And so first off, what am I asking about? Well, there's two things I could be asking about here. I could either be asking about the frequency of the object, or it could be asking about the angular velocity of the object. And so rate of rotation is not a good enough term actually to get to the answer, because that could mean either of these two things. I'm going to show you how to solve for both of them. So frequency, script F, I know that's the same symbol as friction, but we're going to deal with it because, and then angular velocity, that's that new thing we learned, omega. All right, cool. So frequency is how often does a cycle or circle or occurrence occur per unit time, specifically seconds. So it's cycles per seconds, circles per seconds, oscillations per seconds. Angular velocity, though, omega, is the angles swept out per second. So it is radians per second. So that's an important thing to note here. So this is cycles per second, and this is radians per second. So they're not identical terms. So what I know here is the speed, right? Meters per second. How many meters per second is this thing going? Well, here you go. This object is going around in this circle. As long as it's going in a circle at a constant speed, so if at a constant speed, I can say that that speed, v in this case, along the tangent, is equal to distance over time, as long as it's a constant speed. So the distance this thing travels is the circumference, 2 pi r, and the time for one rotation or one circle is the period. So that's the symbol for period. Period is this weird looking T thing here. So that's the time for one cycle, circle, rotation, oscillation, what have you. All right. And so that's helpful there. So I can find out the period of motion now. So the period of motion is 2 pi r over square root of mu sub s gr. And I would want to make that a little bit better, because that's going to be 2 pi r to the first over the square root of r. Means that the square root of r on the denominator cancels and end up with r, the square root of r over mu sub sg. All right, cool. So how can we use that now to get the things that I want? Well, frequency is the number of oscillations per second. Period is the amount of time per oscillation. So period and frequency are inversely related to one another. So therefore, the frequency here would be 1 over 2 pi times the square root of mu sub s g over r. All right? So that's an equation that we want to know here. By the way, this is an equation we want to know here. And then how about omega? Well, omega is equal to the number of radians per second. So here we had one rotation in the numerator. Here I'm going to have 2 pi radians in the numerator, and then the period in the denominator. And so you can see what that does is it gets rid of the 2 pi, and I'm just with mu sub s g over r as the answer for the angular velocity. Okay? Now, if you notice, so there's another relationship, by the way, that there seems to be a relationship between these two as well. Here I have mu sub s gr. Here I have mu sub s g over the square root of r. Well, if we look at how those are related to each other, it's like if I multiplied omega by r, I would get v sub max, or the tangential velocity, because remember, this is a tangential velocity. And so there we go. The tangential velocity of any object on a rigid rotating object is r, where it is with respect to the axis of rotation, times omega. And so a lot of little equations there that allow us depending on how these things get phrased. Because in circular motion problems, we often talk about the frequency. Now, this frequency here is actually something called the linear frequency. So if you're being asked for the linear frequency, it's script EF. If you're being asked for the angular velocity or angular frequency, that's omega. The period is there, and here are all the relationships between them. But because V sub t is what's in our net force equations in the radial direction, oftentimes it's a good idea to solve for that first and then translate it to whichever of the other things the problem asks for. So that's just a little housekeeping stuff. Let's go on to the problem. So we were talking about spinning something like a mass on the end of a string in a horizontal circle above your head. Now, just do it, right? Like grab something, put it on a string. It used to be grab your headphones, but now headphones are not on strings anymore, but whatever. What I want you to notice is if you do this, the faster you rotate it, the closer the circle is to the string being perfectly parallel to the ground. It can never be parallel to the ground exactly, for the same reason that we showed the accelerometer could never be parallel to the ground, because we need a vertical component of that tension to cancel out the weight. But if we think about an angle to the vertical, so if I draw this here, so here we go, boom, right? And so I'll just try to draw this in some sort of perspective, right? So this thing is going in a horizontal circle, right? Here is the axis of rotation, okay? If I were to draw this as an overhead view, so this is a side view, and this is an overhead view, we would just see this, which is not very evocative, but there it is. There's some projection of the tension. Very specifically, it's the radial projection of the tension. But it's not the entire tension, because as we showed before, some portion of the tension is going to act upwards, right, in order to cancel out the FG. And the angle that's critical here is not an angle to the horizontal as normal, it's an angle to the vertical, because it's just naturally, if this object was not moving, it would hang straight down at an angle of 0. It's a nice way to define things. And it's going around, it makes some sort of angle, right? So what we want to do here in this problem is, I want to find an expression for the tension, like what factors affect the tension. And then I want to find, well, like what determines that angle that it makes? Because we saw the faster you go, the greater that angle was. I kind of just want to show the relationship between those. And this type of problem really depends on what you're given and what you are asked for. And I'll show you some variance in this. All right, so that's the basic problem. It is a horizontal circle problem, right? And as we said as well, you can do this problem as well by, it gets a bit more complicated if I tilt it, right? Tilt the plane of that circle, and we'll talk about the effect of that. All right, cool. So this is what we have. Let's talk about setup now. I have my free body diagram. The next thing I want to do is put down axes. And so the first axis I'm going to put down is a radial axis, of course. So that's positive R there. Here it is on this one, positive R. We're always going to make R positive inwards in this type of example, just because it's convenient, because we know the net force has to be radially inwards. The second axis I care about here is the y-axis, not the tangential axis. Don't really care about that. Now, if we were talking about this thing as it was speeding up to a specific velocity or a specific speed, then yes, we would have a tangential component. So actually t would be very complicated, because not only would it have a radial component, not only would it have a y component, it would also have a tangential component. Because actually, this thing is not a rigid object, because this mass kind of lags behind a little bit as you're trying to get it going. It doesn't lag anymore once you are at a constant speed around. And so this is problem can get a lot more complicated if we talk about the transitional states. So right now, at this level of physics, we're not going to talk about that transitional state. We're going to talk about once it's reached that equilibrium in the vertical direction, it's not moving up or down, it's kind of at where it's going to be. So you see, this course, we are not going to full truth here. We are just peeling back some of the layers of lies that we said last year and moving this problem a little forward. So I'm just going to do my sum of forces equations next to the diagram that they are relevant for. But first, I'm going to draw in my components. So I've got my TR here, right? And I don't want to call it TX. It's not an x-axis. It's important. That's a radial axis. And then my TY. Now, some people like to draw the TY here as well, rather than make the triangle. That is entirely your call. I think this is easier, and just in terms of doing the trig, this is probably more physical. So just be aware of that. So if I do sum of forces in the y direction is equal to MAY, I've got TY minus FG equals MAY, right? And then for T, in this case, cosine theta is equal to mg, because AY goes to 0. Remember, we are in that, not in that transitional phase. We're at the phase where it is at a constant height, because it is no longer getting to the angle that it's getting to. So that's a stipulation of the problem that's important. So it looks like the tension here is equal to mg over cosine theta. So let's just think about that for a second. I think that makes sense, that the more massive the mass is, the bigger the weight is, the greater the tension is going to be. Like that just makes sense. That cosine theta is really interesting. So theta is equal to, well, theta when it's 0, right, is equal to 1. So that means that when the angle is 0, meaning flat down, the tension is equal to mg. Of course, that makes absolute sense, right? Here's the thing, it's never going to deviate from there unless it's going around in the circle. So going around in the circle means the tension gets greater. So as theta increases, cosine decreases, meaning the tension gets larger and larger and larger the greater that angle is. And that makes sense, because the faster and faster I go, the greater that tension is as well. Those two things gel really nicely. It also proves to us our notion that theta cannot be 90. It can approach 90, but can never be 90, because at cosine of 90, you get a 0 in the denominator and the whole thing explodes. So no bueno. Here, sum of forces in the radial direction is equal to MAR. And so here, just the radial component of the tension is equal to mVT squared over R. All right, cool. Let's bring that down one level. T, now here looking at that, sine theta is equal to mVT squared over R. All right, so now what you do with this problem is very much a function of what is asked in this problem, okay, and what we care about. So I'm going to take one more step here, because I think it's the most obvious step to take here, and then we can kind of go from there. So there's two things I can do here. I can plug my t into this t and then move things around. Or with this and this, I can divide these equations, right? We have similar number of terms on both sides, 1, and we have a common structure. The left side has t's, the right side has m's. So you can divide these equations. I kind of set it up to plug it in, so I'm going to do that. So mg over cosine theta times sine of theta is equal to mVT squared over R. The masses cancel, okay? And so on the left side here, so now it depends on what I care about and what I need. But the way this looks right now, the left side here collapses to tangent of theta is equal to, or g tangent of theta, VT squared over R, okay? So if we look at that, it seems like theta is a function, right? That angle it makes is a function of how fast it's going. And that should make sense. But this R term is really interesting, because R is the radius of the circle, okay? Right? R is the radius of this circle. But notice here, on this picture, the length of the string, if we call that L, is not the same thing as the radius of the circle. The radius of the circle itself is a function of what theta is if I'm given the length of the string, right? This radius is not a fixed distance, because the faster I go, the higher that goes, theta changes. Now, in some problems, it wouldn't change, but here it very much does. So we're going to deal with that right now. So to look at this geometry, and that's something really important to remember, folks, that the circle is what matters. It doesn't actually matter what this string length looks like. You have to draw in or have a sense of where the circle is, or you miss this geometry. It's a common geometry in a lot of these problems. So it would seem that the radius here would equal L sine theta, sine because the radius is on the opposite side of that, right? So let's see what that does to our expression down here. Okay. That means I've got G, and I'm going to actually put this back into sine of theta over cosine of theta because we're about to introduce another term. Actually, did I mess that up? I think I messed that up. Sine of theta is equal to R over L. No, RL sine theta. Okay, great. So let's see what we can do with this then. Okay. I'm just checking. Cool. All right. So yeah, here we go. I've got VT squared over R, which is L sine theta. And you can see that the expression here is just going to get a little bit nastier. So there you go. And we could solve for VT there. Now it's in terms of L, and there you go. Other things that I can do in this, right, depending of what's going on. VT, well, actually, let's just solve it. VT squared is equal to GL sine squared theta over cosine of theta. And then I can solve for VT if I wanted to. So VT here is radical GL sine squared theta over cosine theta. Not the neatest looking expression, but there it is. Once again, that VT is a function of what that angle is. So there's one and only one VT that allows you to be at that one and only one angle, right? So it kind of, like I said, depends on what you want, because what happens if the question is not about speed, but about the period of motion? Then I would have to substitute in for VT, right? We would know that VT is 2 pi R over the period, but R is equal to L sine theta, and then things start canceling out again. So it kind of the problem is depending, once again, on what it asks for, because it could ask for the frequency or the angular frequency. So we have to just see what's going on. But a couple of important things here. The angle is not dependent clearly on the mass. The speed is not dependent upon the mass, but the tension is dependent upon the mass. That there's a relationship between that angle it makes and how fast it's going around and the length of that string. Those should all make sense, okay? And so that's a typical horizontal problem. Now, I did want to talk about what happens if I tilt that circle. Well, if I tilt that circle a little bit, right, I'll just draw it here. Okay, notice here what that does is it does some really wacky things with components, because the first component here will be a radial component, but now the second component, our like y-axis, is going to be parallel to that axis. It looks like we're just going to have more components in this problem. Okay, so just something to watch out for, and we would have to know like some geometry here in order to figure out what that radius is, given like the length of the string. Okay, so it just changes the geometry and just makes for more components. And that's just generally what tilting does. Tilting causes components. All right, so now let's talk about vertical circles. And I want to talk about two very simple type of vertical circles. We're not going to belabor the point here too much. We're going to talk about the mass on the end of a string, right? So just this, right? Nice and simple. Notice here, it makes a circle, and if I go too slow, it falls down. You can do that for yourself. You could also whirl it in a circle. Notice that the faster you whirl it, the greater the tension is, but where does the tension feel greatest? Hopefully what you're noticing is at the bottom, not at the top, right? The top, it feels least. At the bottom, it feels most. And so if I was going to do that vertical circle here, if I'm looking at the mass at the bottom, looking at the mass at the top. So at the bottom, I've got Fg going down and tension going up, right? Here, I've got Fg going down, and because of just the way the world works there, right? The tension there also acts downwards, which is kind of weird that you have two forces acting downwards, but it doesn't fall. Because remember, it is moving horizontally at that moment instantaneously, assuming it's going around counterclockwise. So it's trying to go along that straight line, and these forces are tugging it downwards. But if it's going sufficiently fast in that direction, those forces are only able to change its direction to continue it along its path, not pull it straight downwards. Okay, so what does this unit tell us? This unit tells us sum of forces in the radial direction. Positive R is radially inwards, right? So at the top, it looks like my sum of forces in the radial direction is equal to MAR is FG plus T equals MVT squared over R. And at the bottom, okay, sum of forces in the radial direction is equal to MAR. It's T minus FG is equal to MVT squared over R. And there you have it. And then I can solve. Now, we now know there's kind of two things that can happen physically, right? If the tension is constant in this, then the speed is not constant, right? But I can keep the tension constant, or the tension changing, and keep the speed constant in this, depending on how physically the problem is phrased. The other thing you can notice is if I am going at a constant speed, the argument I made before about the tension being greatest at the bottom, yeah, because I'm going to add over FG onto this side. But here, if the speed is constant, I would be subtracting FG onto this side, showing that the tension at the top is always smaller than the tension at the bottom, assuming constant speed, right? And we also said we had a problem potentially with at the top about if I don't go fast enough, meaning that there exists a minimum speed I need to be going to go around that corner. Minimum speed, what am I going to do? Hopefully you're thinking to yourself, take a limit. Yep, I can take the limit as V approaches, so there's a couple of limits here. V approaches V min in this case, but that's the same thing as, well, what happens with the tension? If you go too slow, what you'll notice here is the tension, like the rope, goes slack. Well, another way to say that is tension goes to zero, right? So either of these two limits on this expression, Fg plus T equals mvt squared over r, yields the same result, and I would get Fg, which is mg, plus 0 equals mvt, in this case, min squared over r, m's cancel, and I've got the square root of gr is equal to vt min. Well, that's so weird. We have that square root of gr thing popping up again. We saw the square root of gr in a couple of places. We saw that here, right? As part of the maximum speed expression to go around that. We saw that, I don't know, here, because GL sine theta, that's gr. Square root of gr popping up all over the place. Sort of interesting. Vertical circle problem, that should be review. Here's what's not review. Last year, we didn't talk about what happens when you're not at the top or the bottom. But that's easy for us now, because we know the first thing I'm going to do is I'm going to put down a radial axis, positive r, and the second axis we care about in this case is a tangential axis. So let's say we call this the positive theta axis, because that's how we talk about tangential. And then I can put in components. And so this is FGR, and this is FG theta. And then depending on how theta is defined, will determine my trig from here, because I could define theta from a horizontal, or I could define theta from a vertical. I don't want to go into that because it'll depend from there. So you'll notice here on the side, if I were to do sum of forces in the radial direction is equal to MAR, I would get T minus FGR equals MVT squared over R, okay? And so I could find the tension, I could plug in here. It would all depend on what you're given and what you care about, okay? Notice here that same thing, but if I'm up here at this position, I've got T, but now here's FG, and if I were to draw in those components, once again, I would have FG T and then FGR, like that. And then up here, I would have T plus FGR is equal to MVT squared over R, right? So we just kind of have to roll with the punches with what I need during any particular time. So vertical circle problem. The only thing we're adding to this is dealing with what's happening not at the the center. So let's just talk about that tangential component for a second. This would be, if I had a constant tension, what that tangential force would be doing would be speeding the object up as it's going down this way and slowing it down as it's going up. But if the tension is not constant and the speed is, the only way for that to work is if I actually have a component of the tension along the tangent as well, which is actually what happens if you're not going at a constant speed around. That if you're trying to speed it up, what you end up doing is like pulling it, and so there's a lag in the rope, right? Rather than let's say what it looks like perfectly, that the rope, when I want it to be horizontal, is not exactly horizontal. There's a tilt in it. So my hand is moving to create that lag in the rope. That's what creates a tangential component of the tension to either speed up or slow the object down. Once again, that is a lot more complicated, and we're not going to do that, which is why I'm generally doing here changing tension, constant speed, in order to sort of not deal with that. But it does give us these tangential components of the force of gravity. We're going to be kind of a bit squidgy with them. All right. The other variant on the vertical circle problem that you should be familiar with is the roller coaster problem. I'm not going to get too far into this, but there we go, right? It doesn't make perfect circles here, but each segment of this, we can say, is part of a circle, right? I could actually draw a circle to represent any section of this, right? Like, let's say I cared about it here, I can draw this circle that's approximated at that point, whatever it is. That's an approximation, is totally valid. We're going to deal with these three at the moment here, okay? Here, Fg, but now instead of a tension, what we have is a normal force, right? Either the track pushing up on the car or the seat of the car pushing up on the person, depending on what you're drawing a free body diagram for. This seems to have the same free body diagram. This one different because I'm upside down, right? So the seat is actually above my head, pushing me downward. But I don't care about downward here. What I care about is inwards and outwards. Here, there's positive R, same free body diagram, but now the circle's under you. And so there you go. So if I'm looking at this, then sum of forces in the radial direction is equal to mvt squared over r. This is Fn minus Fg is equal to mvt squared, over r. Sum of forces in the radial direction is that's A, R, MAR, and that's now Fg minus Fn equals mvt squared over r because of where the force is with respect to the circle. And here, sum of forces in the radial direction is MAR. I've got Fg plus Fn equals mvt squared over r. So let's talk about a couple of these things. First, normal force. Identities of the normal force. I'll write this down here. Fn. Fn is obviously the force of the track on the cart or the force of the seat on the person, but Fn has a couple of different identities. One is something called the apparent weight. Hopefully you talked about this last year. You don't actually experience your force of gravity. What you experience is the normal force. And the normal force informs you how heavy you feel, right? Because if I'm not accelerating, Fn is equal to Fg if I'm on a flat plane, right? But the second I'm accelerating upwards, Fn's got to be larger than Fg, meaning I feel heavier. And if I'm accelerating downwards, then Fg has to be larger than Fn, meaning I feel lighter. So apparent weight is the notion of Fn. It's not your actual weight. I would never equate that to mg and like calculate an apparent mass. No. Mass is about inertia. Inertia doesn't change because of this. Just our perception of the force of gravity does. Another thing we can say is the reading on the scale. When you step onto a bathroom scale, it doesn't actually tell you your weight. It tells you your normal force. How do I know that? Very simple. Step on a scale, jump up and downwards. Did your weight change? The force of gravity due to the earth? No. What changed is how you're pushing on the scale, which is why the scale reading changes. If a scale read your weight, it would not change as you jumped up and down. Simple proof. All right, going back to this. So what's happening here is on a roller coaster is designed to manipulate your perception of your weight, right? Because usually what we're doing here is solving for Fn. And Fn here is a function of how fast you're going through those sections and the radius of those curves. So there you go. couple of danger points. Here, worried about falling off. Here, if I go too slow, I fall off. So here, I might think about taking a limit as v approaches v min. What does it mean to fall off? Well, the normal force is the force of contact. So if Fn goes to 0, that's the same thing as losing contact. And so I'm going to write that here. The limit as Fn approaches 0 is always the analysis what we want to do when the problem talks about losing contact. Okay? That's super critical. So we're worried about too slow here. Here, I'm not worried about going too slow. If I go too slow, I don't get up the hill or just like stop. Very boring, right? But if I go too fast, boom, off that thing flies. So I'm going limit as v approaches v max here, which is the limit as Fn approaches 0 as well. Once again, losing contact. And I could find out how fast I can go without flying off here, or how fast I can go about with falling off here. Flying off, falling off, two different things. Notice here I'm on the outside of the circle. Here I'm on the inside of the circle, v min, v max. There's a reason for that. Down here, I'm not worried about losing contact. That's just not the worry. I will say, though, that there is a physical, biological worry here. If you're going too fast and the normal force is too great, your apparent weight is too great, you actually black out, right? So there is a limit about how fast you can go. The limit here would be the normal force being about 8 to 10 times your weight, right? And so that's something that comes up as well. A measure of your apparent weight is actually sometimes called your g-force, right? You might have heard of that before. It's not a force, it's actually a fictitious force, right? Because we're in an accelerated reference frame. The cart that we're in is accelerating. So we're going to feel those fictitious forces. G-force is a relative measure of the strength of those fictitious forces. The way we find the g-force is we go the ratio of Fn to Fg. And so if I'm pulling 8 Gs, that means that my normal force is 8 times my weight, and I'm going to black out very quickly, probably like in about a quarter of a second, right? If you want to do some investigation about that, there's a lot of interesting little clips online about G-forces and astronaut training and fighter pilot training and stuff like that. But there we go. We've talked about horizontal circles and variance on those. We've talked about vertical circles. And then in class, we're going to do some more horizontal circles, interesting stuff with a little bit more complexity. So there we go. Now I've got to stop the screencastify.